Okay, so this is the walkthrough for question 4. So this question is about energy transfers. Here are some words used to describe energy. All right, so we've got some stores of energy like elastic, potential and chemical. Okay, and we've got some pathways. Okay, well, we've got energy that is being transferred from one store to another. And remember, kinetic, although it's to do with movement, okay, that's the energy that is stored in an object that is moving. So a cyclist uses an e-bike that contains a battery and an electric motor to commute to work each day. Use words from the box at the top of the page to complete the table below, and you can use each word once, more than once, or not at all. The first one's been done. So in the headlight, we've got electrical energy is being transferred, or in fact, energy is being transferred along an electrical pathway to a light pathway or a radiation pathway. Okay, in the electric motor, okay, so we've got electrical energy there is being supplied to the motor, and the useful energy out is kinetic. Okay, what we want is to get that motor moving, okay, and turning. So that's going to turn the axle of our bike, and which in turn is going to turn the wheels. Within the battery, okay, in the battery we've got a chemical store of energy, okay, and that is going to be transferred usefully into electrical energy. Okay, and then the brakes finally. All right, well, the whole point of putting on the brakes is to get rid of all that kinetic energy. Okay, we're going to stop the bike moving. And where is that energy going to go? Well, it's all going to go into thermal energy. Okay, as those surfaces rub against one another, we're going to get a transfer of energy into the thermal energy store of the tyre, the road, the brake pads. All those things are going to heat up a little bit because of that friction between the moving parts. Okay, part 2. In 1 second, the electric motor gets 250 joules of energy from the battery, and only 175 joules of this energy is used to turn the wheels of the bike. The rest of the energy is wasted. Okay, and what we want to calculate is the efficiency. So our 250 joules of energy is the input energy, okay, and the 175 is the useful energy. So efficiency, we're going to calculate by taking the useful energy transferred, okay, and dividing that by the total energy input. Okay, so our useful is 175, our total is 250. So I need to use one of Miss Williams' funky pink calculators to calculate this. So we've got 175 divided by 250 equals, okay, 0.7. All right, if we want to, we can convert that into percentage by multiplying by 100. So our answer could be either 0.7 or 70%. Okay, so that transfer was, that motor was 70% efficient. Okay, second page, questions. The cyclist and their bike have a combined mass of, okay, let's use the Heist technique again. So we're going to say that's our mass of 80 kilograms. The cyclist rides their bike to the top of a hill that is 12 meters higher than where they started from. So we've got a change in height there. Calculate the change in gravitational potential energy. Okay, so change in GPE is the thing we're looking for. Okay, as the cyclist and their bike moves from the bottom of the hill to the top of the hill. Okay, it says give your answer in kilojoules. Okay, so I'm going to underline that so that I know that I have to do that conversion into kilojoules right at the end. Okay, so the formula for gravitational potential energy, or a change in gravitational potential energy, is equal to the mass multiplied by gravitational field strength multiplied by the change in height. Okay, so we're calculating GPE, so that's what I haven't got. Our mass is 80 kilograms. The gravity is 10 newtons per kilogram, and the change in height is 12 meters. Okay, so I'm going to clear that. I'm going to multiply 80 by 10 by 12, nice easy numbers. Okay, which gives us 9,600. So my answer is 9,600 joules, but we need to convert that into kilojoules. Okay, so that is 9.6 kilojoules. Just dividing that by 1,000 gives us 9.6 kg. Okay, the cyclist rolls back down to the bottom of the hill. The kinetic energy stored in the cyclist and their bike at the bottom of the hill is 7,800. So that's our value for kinetic energy. Calculate the velocity of the cyclist. So the thing we're going to calculate is velocity. Okay, at the bottom of the hill, give your answer to 3 significant figures. Okay, just to remind me, I'm going to write 3SF down there so that I don't forget that at the last stage. All right, we've been given the equation. So that's our highlighting done. We've written out the equation's been written out for us. So we're just going to insert our value. So 7,800 is equal to, I like to write that as 0.5. It makes it easier on the calculator. Times mass. Well, we've got the mass of our cyclist and bike up here. It's 80 kilograms multiplied by their velocity squared. Okay, so at this point, you can use an equation triangle if you want to. Okay, you could say that 7,800 is equal to 0.5 times 80 times v squared. Okay, and you're going to work out that v squared is equal to 7,800 divided by 0.5 times 80. Or we can just say 7,800. I want to simplify this side, get rid of that 0.5 and that 80. They're currently multiplying my V2, so I'm going to divide by that. Okay, if we divide this side by 0.5 times 80, we're left with V2 on its own. And if we divide this side by 0.5 times 80, we're getting a value for V squared. Okay, so let's do that bit first. 7,800 divided by, I'm going to use my brackets, 0.5 times, oops, I'm putting in the value already, 0.5 times 80, close my brackets, equals, okay, 195. So V squared is equal to 195, all right? But that's not my answer because that's my value for V squared and I want the value for V. So V is equal to the square root of 195. So again, I'm going to use my square root function. 195 equals, can't read that, so dark in here, 13.964. Okay, so V equals 13.964. All right, but I've been asked to give my answer to 3 significant figures. Okay, so I'm going to round that figure up to a 4. So my value is 14.0 meters per second. Okay, when an object slides down the slope, there is a change in its store of gravitational potential energy because some is transferred into kinetic energy. Explain why the total energy stored in an object at the bottom of a slope will be less than the change in gravitational potential energy stored in it. So what we're saying is we've got maximum gravitational potential energy up here. Again, as you slide down, okay, that energy is going to be transferred into kinetic energy. But this energy is always going to be less than the gravitational potential energy. And why is that? Well, we've got moving parts again, haven't we? So because of friction between the tyres and the grass, okay, friction between the air and the bike and the person riding the bike, the cyclist, okay, is going to be there. We're going to get energy lost to the thermal energy store of the surroundings. Okay, so some energy or some gravitational potential energy is dissipated to the thermal energy store of the surroundings. Okay, done. 30 marks in the bag.